Welcome to another episode of Winning the Rig Game. Don't forget to subscribe, hit the bell, the like button, and post a comment. It would really help me out with the algorithm. As always, this is not investing advice. This episode, we're going to take a deeper dive into AI Day 2. Not all of it, just the last part, the part about Dojo. For me, I felt that was the most significant part. Everyone was concentrating on the robot, but the truth is Dojo is much more important, at least right now. Eventually, the robot will be important, but I felt Dojo was really overlooked.
Why is a car company building a supercomputer for training? And this question fundamentally misunderstands the nature of Tesla. At its heart, Tesla is a hardcore technology company. Tonight we're going to talk a little bit about Dojo and give you an update on what we've been able to do over the last year. But before we do that, I wanted to give a little bit of background on the initial design that we started a few years ago. When we got started, the goal was to provide a substantial improvement to the training latency for our autopilot team. Some of the largest neural networks they train today run for over a month.
In this episode, we're going to take a deeper dive into AI Day 2. Not all of it, just the last part, concentrating on Dojo. I felt Dojo was one of the more important parts and really didn't get the attention that it should have. Why is a car company building a supercomputer? What is the end goal of Dojo? We'll get to that at the end. Basically, it's building a supercomputer to train the full self-driving, autopilot, and eventually the Tesla bot, maybe a couple of other things.
It would take 1 hour, but if you have one GPU, it would take 100,000 hours. So that is not a humane time period that you can wait for your training job to run, right? We want to ship faster than that. So that means you're going to need to go parallel. So you need more compute for that. That means you're going to need a supercomputer. So this is why we've built in-house 3 supercomputers comprising of 14,000 GPUs, where we use 10,000 GPUs for training and around 4,000 GPUs for auto-labeling.
What is a neural network? A neural network is a series of algorithms that endeavors to recognize the underlying relationship in a set of data through a process that mimics the way the human brain operates. This is what makes what Tesla is doing very different from other robotics companies. Tesla is a car company. It's also an AI company. No other quote-unquote car company is building supercomputers. Why does Tesla need to build a supercomputer? In this episode, I'm going to comment on a few clips from AI Day 2.
Yeah, let's talk about auto-labeling. So we have several kinds of auto-labeling frameworks to support various types of networks. But today, I'd like to focus on the awesome LanesNet here. So to successfully train and generalize this network to everywhere, we think we went tens of millions of trips from probably 1 million intersection or even more. To solve this challenge, we've tried various ways of manual and auto-labeling. So from the first column to the second, from the second to the third, each advance provided us nearly 100x improvement in throughput. But still, we want an even better auto-labeling machine that can provide us good quality, diversity, and scalability. To meet all these requirements, despite the huge amount of engineering effort required here, we've developed a new auto-labeling machine powered by multi-trip reconstruction. So this can replace 5 million hours of manual labeling.
The current state GPU clusters. Tesla already, before Dojo, had 3 supercomputers. They're running NVIDIA superclusters, but Dojo is going to be better, faster, cheaper. With the cluster, they were really running into scalability issues. Dojo will allow them to scale up faster and achieve the goals of full self-driving and the Tesla bot and other things. Auto labeling will replace 5 million hours of human labeling. In June, Tesla was able to reduce their headcount by 200. We had an indication what Tesla was looking to achieve was working. Eventually, I think they'll be able to eliminate human labelers.
3D scenes are notoriously slow to produce. Take, for example, the simulated scene playing behind me. A complex intersection from Market Street in San Francisco. It would take 2 weeks for artists to complete.
One of the benefits of Dojo is Tesla will be able to create simulations 1,000 times faster to create special situations to train the AI.
Next, we can use the line data and sweep geometry across its surface and project it to the road, creating lane paint decals. Next, using median edges, we can spawn island geometry and populate it with randomized foliage. This drastically changes the visibility of the scene. Now, the outside world can be generated through a series of randomized heuristics. Modular building generators create visual obstructions, while randomly placed objects like hydrants can change the color of the curbs, while trees can drop leaves below it, obscuring lines or edges. Next, we can bring in map data to inform positions of things like traffic lights or stop signs. We can trace along its normal to collect important information like number of lanes and even get accurate street names on the signs themselves. Next, using lane graph, we can determine lane connectivity and spawn directional road markings on the road and their accompanying road signs. And finally, with lane graph itself, we can determine lane adjacency and other useful metrics to spawn randomized traffic permutations inside our simulator. And again, this is all automatic, no artists in the loop, and happens within minutes. And now this sets us up to do some pretty cool things. Since everything is based on data and heuristics, we can start to fuzz parameters to create visual variations of the single ground truth. It can be as subtle as object placement and random material swapping to more drastic changes like entirely new biomes or locations of environment, like urban, suburban, or rural. This allows us to create infinite targeted permutations for specific ground truths that we need more ground truth for. And all this happens within a click of a button. And we can even take this one step further by altering our ground truth itself. Say John wants his network to pay more attention to directional road markings to better detect an upcoming captive left turn lane. We can start to procedurally alter our lane graph inside the simulator to help create entirely new flows through this intersection to help focus the network's attention to the road markings to create more accurate predictions. And this is a great example of how this tooling allows us to create new data that could never be collected from the real world.
Cerberus Systems, another wafer-scale AI chip hardware maker, has a valuation between $1 and $10 billion. If Tesla's Project Dojo was a spin-off company that could create a supercomputer at 1/6 the price of an NVIDIA-scale supercluster, it would have an unbelievable valuation. Once again, Wall Street is missing this. If this was a well-funded startup, it would be receiving a much higher valuation.
Now, the system tray is a key part of realizing our vision of a single accelerator. It enables us to seamlessly connect tiles together, not only within the cabinet, but between cabinets. We can connect these tiles at very tight spacing across the entire accelerator, and this is how we achieve our uniform communication. This is a laminated bus bar that allows us to integrate very high power, mechanical and thermal support, and an extremely dense integration. It's 75 millimeters in height and supports 6 tiles at 135 kilograms. This is the equivalent of 3 to 4 fully loaded high-performance racks. Next, we need to feed data to the training tiles. This is where we've developed the Dojo interface processor. It provides our system with high bandwidth DRAM to stage our training data. And it provides full memory bandwidth to our training tiles using TTP, our custom protocol that we use to communicate across our entire accelerator. It also has high-speed Ethernet that helps us extend this custom protocol over standard Ethernet. And we provide native hardware support for this with little to no software overhead. And lastly, we can connect to it through a standard Gen 4 PCIe interface. Now, we pair 20 of these cards per tray, and that gives us 640 gigabytes of high bandwidth DRAM. And this provides our disaggregated memory layer for our training tiles. These cards are our high bandwidth ingest path, both through PCIe and Ethernet. They also provide a high radix Z connectivity path that allows shortcuts across our large Dojo accelerator. Now, we actually integrate the host directly underneath our system tray. These hosts provide our ingest processing and connect to our interface processors through PCIe. These hosts can provide hardware video decoder support for video-based training. And our user applications land on these hosts so we can provide them with the standard x86 Linux environment. Now, we can put 2 of these assemblies into one cabinet and pair it with redundant power supplies that do direct conversion of 3-phase 480-volt AC power to 52-volt DC power. Now, by focusing on density at every level, we can realize the vision of a single accelerator. Now, starting with the uniform nodes on our custom D1 die, we can connect them together in our fully integrated training tile, and then finally, seamlessly connecting them across cabinet boundaries to form our Dojo accelerator. And altogether, we can house 2 full accelerators in our Exapod for a combined 1 exaflop of ML compute. Now, altogether, this amount of technology and integration has only ever been done a couple of times in the history of compute.
Dojo hardware. Dojo hardware has shown an unbelievable pace of innovation. As far as I know, in the United States, there are only 2, or supposedly 2, exascale supercomputers. One, the Frontier system with Department of Energy, and supposedly the NSA has one.
The Bastrom mean and standard deviation values. Die-local reduction followed by global reduction towards the middle of the tie, then the reduced value broadcast radiating from the middle, accelerated by the hardware's broadcast facility. This operation takes only 5 microseconds on 25 Dojo dice. The same operation takes 150 microseconds on 24 GPUs. This is an orders of magnitude improvement over GPUs. So when we set out to tackle real-world workloads, we looked at the usage patterns of our current GPU cluster. And 2 models stood out: the auto-labeling networks, a class of offline models that are used to generate ground truth, and the occupancy networks that you heard about. The auto-labeling networks are large models that have high arithmetic intensity, while the occupancy networks can be ingest bound. We chose these models because together they account for a large chunk of our current GPU cluster usage, and they would challenge the system in different ways. So how did we do on these 2 networks? The results we're about to see were measured on multi-die systems for both the GPU and Dojo, but normalized to per die numbers. On our auto-labeling network, we're already able to surpass the performance of an A100 with our current hardware running on our older generation VRMs. On our production hardware with our newer VRMs, that translates to doubling the throughput of an A100. And our model showed that with some key compiler optimizations, we could get to more than 3x the performance of an A100. We see even bigger leaps on the occupancy network. Almost 3x with our production hardware, with room for more. So what does that mean for Tesla? With our current level of compiler performance, we could replace the ML compute of 1, 2, 3, 4, 5, and 6 GPU boxes with just a single Dojo tile. And this Dojo tile costs less than 1 of these GPU boxes.
Whoa.
What it really means is that networks that took more than a month to train now take less than a week. It occupies 4,000 GPUs over 72 GPU racks. With our dense compute and our high performance, we expect to provide the same throughput with just 4 Dojo cabinets. And these 4 Dojo cabinets will be part of our first Exapod that we plan to build by Q1 of 2023. This will more than double Tesla's auto labeling capacity. The first Exapod is part of a total of 7 Exapods that we plan to build in Palo Alto right here across the wall. We believe that we can get another 10x improvement with our next generation hardware.
No one else is going to be able to achieve this because they can't just buy what Tesla did. At the beginning of the video, I asked, what is the end goal of Dojo? The main goal of Dojo is to reduce the training time of the neural networks from 1 month to 1 week. By having 7 Exapods, they'll be able to reduce the neural network training time once per day. And they even said that there's a chance of up to a 10 times improvement in what they're currently doing. That would be able to get them down to about 2.5 hours to train a neural network that is currently taking a month. That is why Dojo is significant. There are all sorts of possibilities with artificial intelligence. It's coming and it's going to change the world. Eventually, they might even achieve artificial general intelligence.